joint work with a visiting researcher from Germany who stayed with us for 6 months. And yeah, unfortunately, he needed to leave Australia again. And with the time difference, yeah, I'm also presenting on his behalf right now. His name is Philip Bauer. And just to give you an idea, yeah, how he looks, yeah, that's him. As I said, this research is part of program 3 on designing socio-technical robotic systems. In this program, we address different aspects. So, for example, we touch on human factors in collaborative design. We touch on AR, VR, so augmented reality, virtual reality, as well as on socio-technical factors, on how to basically bring together the social and the technical side of cobots. The overarching goal of program 3 is to support organizations in adopting cobots. And here, we don't work in isolation. So basically what we try to do is to bring together all the insights and all the great research from all the other programs in the ACC and turn this into kind of a guideline which companies can apply in the end. So a simplified process could look like the following here. So first, it's about analyzing the existing workplace. Second step would be to understand the complex interdependencies between the new cobot, which should be adopted, but also how it is affected by the existing workplace in terms of space, in terms of the processes, but also in terms of the objects which need to be manipulated, but also the workers involved in the workplace, the overarching organization, etc., etc. And based on this, new socio-technical cobot workplaces should be derived. So here's also the idea to have alternative settings, which we then simulate using AR, VR in order to identify the most suitable ones, but also to get workers and other stakeholders involved as early as possible to incorporate the feedback, the expertise to really develop the most suitable system, but also to ensure that there is stakeholder buy-in and stakeholder support so that everybody knows what's coming, so they're not surprised by suddenly having this machine standing in the middle of the workplace. And then in the end, of course, it's also about implementing this cobot workplace. A key aspect with cobots is safety. So how can we do this in a safe manner so that the cobot doesn't injure or damage people and other equipment? And today's focus will therefore be on how can we support organizations in assessing and mitigating safety risks. So that's just to set the scene. Before we jump into this, a couple of words on what actually is a cobot. On the left side, we see a very simplified taxonomy. When we talk about a cobot per se, it's usually just a cobot manipulator. So to say the cobot arm in the control system, which is an incomplete machine. So in order to do something, it needs a tool / an end effector and also an application. And additional equipment like safety equipment, which in the combination forms the cobot system. But then, of course, the cobot system doesn't work in isolation, and usually it's part of an overarching workplace, which involves physical space, but also processes, humans, work ethics, etc., etc. On the other hand, in order to differentiate robot from a cobot, we also need to look at the level of interaction. And here we have different frameworks available. So that's just one which we found quite useful in program 3, but of course there are also other ones. So when we talk about cobots, we usually focus on the 2 levels of interaction on the left side. So really something in collaboration, so robot and human work hand in hand, or a cooperation where they, for example, hand over work pieces, but do different tasks, but at the same work piece. But we don't talk so much about the coexistence or a traditional robot when it's isolated in a cell. if you're interested in a more detailed discussion about what's a cobot, what's a robot, I included a QR code on the upper right side, which links to a conference paper which we published earlier this year, where we developed a draft definition of a cobot which goes beyond a manufacturing cobot and also tries to incorporate, for example, service robots. But yeah, this would lead a little bit too far for today. When we talk about implementing and adopting cobots, there are already a couple of international standards and also Australian standards which address the aspects of general safety of machinery, the safety of industrial robots, but then also some which focus already on cobots. But especially the standards on cobots are in a very early stage. So unfortunately, there's not a generally applicable guideline out there which organizations can use in order to adopt cobot. So this was also the starting point for an associated project to the ACC. So it was a project funded by the Centre for Work Health and Safety in New South Wales, where we developed a guideline to support companies in designing a safe cobot workplace. So you can see some snapshots what we did here. So we developed safety flyers, which really explained some of the key aspects in a hopefully understandable way. But we, for example, also provided guidelines and checklists to assess different safety or risk factors, and also provide a list with suitable safety measures. Also here I included a QR code. And the tool I want to present to you today basically builds on what we did in this project. So the underlying of the idea of this prototype tool is to support organizations in doing a risk assessment. So even though we have a good starting point with the guidelines I just mentioned on the previous slide, there's still a little bit the challenge that organizations have a workplace and then they need to do a risk assessment to basically identify risks and also mitigation measures. But often this is kind of a big jump and requires a lot of expertise. And so our idea was actually supporting organizations by splitting this big jump into smaller steps, which are better manageable and might be less overwhelming, and also with the idea that we can provide more detailed support for all of the individual steps. And that's basically the underlying idea of the tool I will show you in a second. But the important thing to mention here is that our goal is to help organizations navigate this process, but not to automate it, because each workplace is more or less unique. So it would be kind of a dangerous activity to have this, an automated tool which tells you what you need to do and what you shouldn't. So it's really to provide guidance to navigate this complicated or complex process of a risk assessment. The tool itself has different user inputs. So the user can input or specify what's the cobot or the robot application/task. What's the level of interaction? So is it a close collaboration or is it more like a cooperation or coexistence? But also what's the level of autonomy? So does the robot just follow an offline programmed program and the only interaction with the environment is that it stops? Or do we have some level of intelligence in the system so the robot can identify different situations and react accordingly? And also, what type of robot are we looking at? So here we just differentiate between an industrial robot and a cobot. And in the end, we have different outputs. So we have different risk factors. So basically the causes of hazards. We have risks. So basically what's the resulting consequence, including the severity and the probability of these hazards. And the tool also provides you with some indication or some suggestions and recommendations what safety measures would be most suitable. I don't go too much into the mechanics of these tools because this would probably turn into a 3-hour lecture. Just to invite you, if you really want to learn more about how this tool really works in detail, please just get in contact with me or Program 3. The only thing I want to say about the tool mechanics right now is that we use a matrix-based approach where we can map different domains onto each other. So we can, for example, map different robot tasks and interaction forms onto risk factors, saying, okay, for this type of interaction, this results in or affects the risk factors in a specific way. And it's also possible to weight it. And then with matrix multiplication, we can basically calculate how the robot task affect the risk factors and how this affects the risks and derive suitable safety measures. And we implemented this in Excel, which I have to admit is not the most powerful tool. So it gets a bit complicated at some point, but the intention here was to have a tool which organizations can use quite directly. So they don't need to purchase an expensive license for some specialized tool, but can just use an office tool. But the evaluation showed that maybe we should switch to a more online-based tool. Anyways, that's an overview of the tool. So I will step you through the steps in a second. Just 2 key terms I want to mention right now because that's really important to understand how the tool works. We differentiated risks and risk factors. So risk factors per se are kind of neutral characteristics, but if they have a specific value or property, they can cause a hazard, a damage, an injury, etc. And here we differentiate different domains. For example, we have a robot-specific domain, robot system-specific effectors, application and effector, workpiece, workspace, operator, and organization specific factors. So, for example, if you talk about the workpiece, it could be the weight of the workpiece, which per se is not a problem at all. But if it's too heavy for a robot, it might cause a hazard. Or if the workpiece, for example, is brittle, we might have debris flying around when we combine it with an application like milling, for instance. But this is really kind of an interesting idea we used here because it's really focusing on the causes, which also later on allows us, for example, instead of just fighting the risks, so instead of fighting the symptoms, we can really go to the cause, to the root cause, and try to prevent a risk from happening. A risk itself would be a hazard, but also includes an assessment concerning the severity and the probability. So how likely is it to occur, and also what would be the consequences? Would it mean that somebody dies, or would it more or less result in a small scratch in the equipment? And here we differentiate physical hazards, for example, like collisions or injuries, but also psychological hazards, like what does it mean for me as a human when I suddenly need to work in isolation because all my teammates were replaced by a cobot, or aspects like trust, but also social and ethical hazards, kind of a more overarching aspect of the organization. Okay. So when we start the tool, first thing it asks us to do is to specify what is the robot task, what is the interaction form, what's the level of autonomy, and what's the robot type. For the robot task, we basically derive different categories of tasks from literature. So at the moment, the tool differentiates assembly, cast and molding, cleaning, hygiene, finishing, sanding, welding, soldering, etc. And in addition, it allows us also to specify different processes. So for example, if you have assembly process, is it a screw driving process? Is it press fitting, casting in nuts? Is it wiring, etc.? So here we can already add kind of a level of detail. The next thing, it allows us to specify interaction form and level of autonomy. And here we used an enhanced version in terms of level of interactions. So instead of 4 different steps, we have 7, which works well. But here also in the future, we need to see if 7 is really suitable or if it just complicates things. And also if these levels of interaction would also work for a non-manufacturing oriented workplace. But for example, what we do here is that we also differentiate cooperation in terms of sequential and simultaneously. So for example, if we have one workpiece, does human and robot work at the same time at this workpiece, or does the robot, for example, hand over the workpiece to the human? And on the other axis, we have the level of autonomy. So is it fully autonomous? Or is it semi-autonomous, so it still waits for specific user input? Or is it active or human guided? Or is it passive, so basically the cobot or robot doesn't have any drives and is just limiting the movement. So a little bit like the first cobot by Colgate, which basically just meant that it limited how a human could work a specific joystick around. And then the table also provides some examples to support the users in identifying what type of cobot do they actually have. Based on this, the tool calculates a first draft of risk factor assessments. And here it categorizes the different risk factors concerning the probability, the severity, and also the controllability. So basically meaning how easy is it to change or affect these risk factors. And what it does is that it derives a table on the left side where we can then see an assessment. And of course, this assessment depends on the user input. So it depends really on the application, but also on the type of interaction and the level of autonomy. And usually, not usually, so here the rule is the lower a value, the better. So for example, in this specific use case, the payload or the probability that the payload is causing an issue is quite low. But if it would cause a payload, it would be quite severe, but it would be possible to control it rather well. On the other hand, if we look in this use case, variable movements, the probability is kind of medium. The severity would be low, but in this instance, it would be really hard to control this factor. But it also listens or shows other factors which are blackened out if they are not relevant for this application and use case. So for example, noise or vibration wouldn't be relevant in this specific instance. What it also does is to map them in portfolios, because portfolios are great and help to visually understand complex instances and issues. And here we have different portfolios. So one is the probability and the severity, and the second portfolio focuses on the controllability. And for example, in this, what we can see here are different areas. So on the lower left are things which are less critical. So because the severity is low and also the probability is low. And on the upper right, we have things which, if they would happen, would really severe, and they're also quite likely. And this already helps us to get a sense on where we should focus on our attention. So for example, in this case, ambient lighting would be highly likely to cause an issue. And if it happens, it would have a severe or a medium severity. And the controllability would, medium, meaning we can control it, but it might be complicated in this instance because we might have, or the surrounding factory environment wouldn't allow us to fully control it. And the same we can also do factors like, for example, adequate workspace design or unergonomic postures, just to mention some examples. Now you will probably say, hey, wait, how does the tool know all these specifics? Well, that's kind of the challenge here, to develop a tool which is generally applicable, but still can be adjusted and tailored to specific unique workplace settings. That's the reason why we included this user input opportunity, where users can go through all the different risk factors and provide, to tailor them to the specific workplace. All of the risk factors by default have an average weight of, if I remember well, 5 on a scale from 1 to 10. And depending on the specific workspace settings, the user can go through and say, okay, for me in this specific setting, and based on my experience and expertise, I would say actually this factor has a higher importance, so the user can increase the importance, but the user can also say, for this setting, it's not important at all, so I can ignore it. And one feature we're working on at the moment, which hasn't been implemented yet, is also to decrease the importance, to really allow users to tailor everything to their specific workspace. The next step is then to derive risks from the risk factors in combination with the application and the type of cobot, etc. And the setup is similar to the risk factors, to have some consistency here, to not confuse the user with different ways to present information. And here we can then say, let's see, the Zoom didn't really work. But here we have the same rule, the lower value, the better. So for example, the first would be physical worker injuries, which are not related to a collision. So it might be due to bad posture or bad ergonomics. Or we can say the next one would be really a human-robot collision, or the next one would be human-robot collision based on the interfactor and so on. It really provides us with some indications about where are the most severe risks. And in order to also make this a bit more usable, we are using the same structure of portfolios, where we have basically, in lower left, the risks which are less critical, and on the upper right, we have the risks which would be really critical. And most of you will probably recognize that this setup of using this matrix is also inspired by a failure mode and effects analysis. So we really try to link our visuals to other methods and other tools, which hopefully are already known in most of the workplaces. Just some examples. Skip here. And in the end, the tool also suggests some safety measures in order to mitigate the identified risks. And here we also differentiate between inherent safe designs, technical and additional measures, and user information. So following the UTS 12100. And what was important for us was that we don't filter these measures, but provide more like a ranking, and really enable users to go through the risk measures and say, okay, this tool or the tool would suggest, let's say, for example, use the lowest possible robot size. But this might not be possible in our case. So So let's see what are other safety measures which might have or would have a high impact. So it really tries to bridge this or find a trade-off between providing advice and recommendations, but still allow users to also bring in their own expertise and also to bring in their own assessment of the workplace. So this was quite a quick run through the tool. So I hope I could bring across the message in a kind of a comprehensive and understandable way. But I can also understand that it might have been a little bit too quick in some points. But to conclude is that we have developed this cobot work health and safety guidelines, which help organizations to navigate the design of a cobot workplace, because safety is really one of the key issues in designing a cobot workplace. And even though cobots are advertised as inherently safe, there are a lot of factors which can actually jeopardize the safety of a cobot. And for example, by having unsuitable end effectors or by having an application like welding. And so we hope that this prototype tool will help organizations in identifying these risk factors and also help them to navigate this risk assessment process in an effective and understandable way by splitting this big or usually big task of risk assessment into smaller, better management tasks. And he also initially evaluated this tool in different university settings, also using some of our translation projects in the ACC. And our initial insights are really promising, so it worked quite successfully. But I also need to stress that it's a prototype tool. So in order to be applicable in a more general and wider sense, we need more evaluations in order to check if our assessments are accurate, if our mappings between the, for example, risk factors and risks are adequate, but also to do some fine tuning around the tool. You saw some of the screenshots, the layout wasn't, there's still potential for improvements. Also, there are some terms and definitions which need to be fine tuned in order to be more, or better understandable. So it's a first good and promising step, but there's a lot still to do. So I would also invite you, if you want to learn more about the tool, or if you are interested in applying the tool and helping us to test and improve it further, please reach out to myself or to Program 3. It would be great to really develop a tool which can be applied later on in industry or also in academia. That's it. Thank you.
Cool. I've got a question, Matthias.
Mm-hmm.
Can you hear me?
Yes.
So back to the sort of probability or likelihood of something happening. Have you got are there any tools to help estimate that? Because obviously you can do that when you've got loads of data and you've seen, things happen at this rate. But when it's a new thing, how do you determine that in a realistic way?
That's a very good question. So at the moment, it's based on some evidence we could find in literature, but the main source of data was our assessment.
Yeah.
So that's also something what we really would need to double check with different robot and cobot experts to really ensure that this mapping is sound and robust. But I fully agree that's one of the key challenges when you do such a mapping.
Yeah, that's right. And did you look at any other industries or adoption of technology and how they estimate likelihood of things, going wrong?
Not yet, but it would definitely be a good next step. So to some extent, what we looked into were general risk assessments like the ISO, 31000, and all the variants of it, and also failure modes and effects analysis. Yeah, but there is potential to have a deeper look into other areas.
Yeah. Okay, thank you. There's some questions in the chat if you go to the chat.
Mm-hmm. Okay, so one question is, have you thought about the inverse problem? Meaning, given risk factors and level of risk you're willing to accept, produce, suggest a system that meets those factors? No, we haven't, to be honest. But I mean, since we're using matrix multiplication here, we could easily reverse the process. It would be actually interesting idea. So Fred, if you're willing and open to explore this, we could really see if, what we, could make with it. Oh yes. The next question was if I can share the slides. Yes, definitely. And Marion, correct me if I'm wrong, we also recorded the presentation and also uploaded to YouTube, I guess.
Yeah, that's right. I can send the slides out if you're happy, Matthias, when I send the link to the recording.
Yes. Mm-hmm.
Yep.
Or maybe switching direction of the questions. I'm just wondering, would you be willing to use such a tool in your workplace, or what could be issues you can see of having such a tool? Question for Q&A? No.
Matthias, sorry,
Yes.
I was just waiting for people to respond, but yeah, the tool is quite useful. Primarily, risk assessments are anyway required, and this elaborate tool practically takes a lot of guesswork. I'm assuming without knowing the details.
Mm-hmm.
I'm assuming that it takes a lot of guesswork out of risk assessments, because in risk assessment, typically you have to, if you have a checklist, it's always good. You can tick mark, and the way I believe, you've elaborated it based on some processes, I think it'll be useful. It'll be worthwhile to actually try and contribute to if there are anything required. I had put in a question in the Q&A. Now it was just around, some examples of controllability. So I see that you have modeled it on the FMEA framework. And when it comes to typical risk assessments, we're very used to doing the probability and the severity.
Mm-hmm.
The controllability sounds interesting, but just keen to understand, are you able to unpack that a bit in terms of giving some examples on the controllability factor and how, with those examples, it has affected the risk rating and has potentially helped with, corrective actions?
Mm-hmm. Yes, sure. Sorry, I didn't see it was in the Q&A section, which I can't see. So the idea with the concept, so in a normal failure mode and effects analysis, the third factor would be how easy it is to spot it, that there is an issue. But we thought, we add this aspect of controllability, which really means how easy is it to affect or change a specific risk factor. So, for example, if we, for example, look at ambient light or noise, if we are in a, let's say, indoors factory environment and we have a dedicated room, It's probably quite easy to control these factors because we can install different lights in the room, or we can also insulate the walls in order to reduce noise. But on the other hand, if you think about a more or bigger factory environment where we don't have a dedicated cell or a dedicated room, it might be more tricky to affect light and noise because there might be another station 10 meters away, which is quite noisy, so we can't really affect it. Or if you think about outdoor applications, like on a construction site, it's probably impossible to control light and noise in a sufficient way. But also, so it's affected by the space, but it's also affected by the application. So for example, if we have a polishing task, or let's say an assembly task, it normally means the noise levels are rather low. But if we have a milling task or a welding task, it might be noisier. And depending on what the task or the application is, we might be able to control this noise, or we actually don't have a way to control it. And I hope this makes sense.
Yes, it does. Again, I think I'll need to possibly try the tool.
Mm-hmm.
I'm getting a feeling that are we trying? So there are two layers to any risk assessment. I'm talking about typical risk assessment. One is you assess the risk, identify the hazard, assess the risk. And the second layer is where you start looking at corrective actions to mitigate or remove that risk. So I'm still not 100% sure the controllability part of it, but anyway, I totally get it where you come, where this is coming from. I think best option is let me try the tool.
Yes. Okay. So I mean, from a Sean perspective, controllability assess a little bit the effort. So kind of a cost benefit analysis. So meaning, okay, how difficult it would be to try to change this factor. And if you say, okay, I have two with the same severity and the same probability, but one is more easily to affect and the other one harder to affect, it gives you kind of an indication.
No, I understand the intent behind it. Perfect. I think it just needs to, sort of be tested. Thank you.
Okay. Any further questions? Matt switched on his camera. Feel a bit like being in a lecture, calling people out. And then they usually also dive down and hide behind the desk. Okay, otherwise, thanks a lot for attending my presentation, and I really hope that the basic setup of the tool looks reasonable and valid. But also based on as indicated by most of the questions, the key thing now will be to have a closer look into the mechanics of the tool, evaluate the mechanics, and really make sure that it's sound and robust, and apply it in as many contexts as possible to really ensure that we can use it in a general way, and also double check all the links plus the user interfaces.
I have one question.
Yes.
So how much have you worked with industry partners to sort of come up with this? Have you had many discussions, people using cobots to develop this tool?
Not for this tool. So we had industry involvement in order to develop the overarching guidelines, which you can see on the right side, to develop and design safe cobot workplaces. And based on what we heard in the interviews and through the evaluations, yeah, we got the sense that it would be good to provide more support and break the big step into smaller steps. But otherwise, our intention was to first develop a prototype tool, and then when we have something tangible, approach industry and get their input.
Okay, thanks.
Okay. Maren, shall I close the meeting, or how does this work?
Yep. Oh, good.
Good.
Thank you, Matthias. Nice work.
Thank you.
Thanks, Matthias.
Matthias, if you want to send me the slides, I can PDF them and send them out when I've trimmed down the recording.
Perfect. Thank you.
Great. Thanks very much. That was awesome.
Okay.
See ya.
Bye.